This is a short video on part 2 of L'Hopital's rule. So what is part 2 of L'Hopital's rule? So let's say that I've got real number, or not necessarily real numbers. So I've got a and b, where it's possible a is negative infinity, it's possible b is positive infinity, otherwise a and b are a real number. And let's have two functions, f and g, that are differentiable on whatever the open interval between a and b actually is. And we're also going to assume that the derivative of g is non-zero for every x between a and b. We're finally going to suppose that the limit as x goes to a from the right of g is plus or minus infinity. And so in the proof, we're going to do plus infinity later on. I'll remind everybody of that as we go. But there's two things you could say if all these hypotheses are satisfied. So the first thing that we can say, if it's the case that the quotient of the derivatives has a limit as x approaches a, so it has a limit L, that's a real number, well then the limit of the quotient f over g is also equal to L. And similarly for part B, if the limit of the quotient of the derivatives as x approaches a from the right is either infinity or negative infinity, then the limit of f over g matches that. Cool. So how are we going to prove this? So what we're going to do is we're going to suppose again that the limit of g is positive infinity. You could do a similar kind of arguments that I'm about to do if g was negative infinity. And so what else do I know? Well, if alpha and beta are two real numbers that are between a and b, where alpha is to the left of beta, then I know g of alpha cannot be equal to g of beta, and that's because of Rolle's theorem. And so to remind you of that, what do we assume about g? G prime is never zero for any real numbers between a and b. And so, right, where does Rolle's theorem tell me? Rolle's theorem told me that if these things did match, then there would have to be some point where this did equal 0, which is not true. So therefore, I can assume that these two outputs are different. So what then happens? I can use, remember, the Coachee mean value theorem, which told me that f of beta minus f of alpha over g of beta minus g of alpha should be equal to f prime of u over g prime of u for some u between alpha and beta. And that'll be useful going forward. So now let's get into our cases. We're going to try to prove case A. So case A. So we get to assume that the limit of the quotient of the derivatives is this number L. So let's suppose some things about L too. So let's suppose L is greater than 0. And so let's think about what does it mean to actually have this kind of in our hand to help as a tool. So, well, for epsilon that's bigger than 0, we should be able to find some number c between a and b such that this difference here should be between L minus epsilon and L plus epsilon. Again, as long as A is less than alpha, which is less than beta, which is less than or equal to C. So in other words, take C close to, maybe you need to take C closer to A in order to make sure you get within epsilon here. So this kind of idea is foregoing the usual delta notion that we might be used to. So we're just saying there's some point close enough there such that this always happens for every real number between a and that c. So what we're going to do is we're going to think some more. What else can I say? G of x goes to positive infinity. So what can I assume then? Well, if c is kind of the farthest right that I'm looking for right now, and maybe I need to take c closer to a, I can guarantee that I can pick the right c so that g of c is going to be a positive number. So let's consider the case where this beta is actually equal to c, kind of that right endpoint. So let's just replace these betas by some c's. So that's not too bad. So now the same thing holds where alpha is a real number between, I see that should be in a and c. And now let's think about what else do we know. So what happens as the input alpha approaches a from the right? Well, g of c is a fixed number, and g of alpha, well, if alpha is getting close to a, remember I had this assumption that the limit of g goes to infinity. So that means this fraction should get small, should go to 0. So what we're going to do is we're going to assume, right, eventually then, I could also take c smaller if needed to guarantee that this fraction should be just some number between 0 and 1, right? So I'm saying this fraction should get arbitrarily small. Just take c even closer to a if necessary to make sure that fraction is between 0 and 1. So what can we say about g of a minus g of c over g of alpha? Sorry, that's an alpha right there. I could simplify that. That's 1 minus g of c over g of alpha. But if this is a number between 0 and 1, then I know that this is, in particular, just positive. So this quantity is a positive number for all alpha between a and c. And what we're actually going to do with it is we're going to take this number here, and we're going to multiply it through this inequality here. And the whole point is that when I do that, I've just justified that none of the inequalities turn around. So let's do that. So there's me multiplying this positive number through all those inequalities, and notice that all the inequalities stay, right, because it's a positive number. Now what we're going to do is we're going to simplify a few things because, you know, it's looking pretty nasty. But I'm going to rewrite this just here. What else? I see that these are opposites of each other, so when they cancel, you should get a negative. So that would flip the signs on these. So that's why you notice f of alpha is now positive. And then what would you have left? If these are gone and if these signs are flipped, then each of these just has a g of alpha in the bottom. So think about that kind of college algebra simplification in the middle. And I didn't do anything special on the right. It's the same, just this is 1 minus g of c over g of alpha right here. Okay, so now let's think about what do we know about these again? And what do we know about this again? Well, remember, like g of c and f of c is a constant. We're kind of treating alpha as the variable right now. So I know that, well, both of those should go to 0 as alpha gets close to a from the right. So what does that mean then? So let's think about another way to say that. So given a number delta that's between 0 and 1, and this delta that I'm playing with is kind of functioning as like an epsilon in the limit definition of each of these. Anyway though, so given any delta, such that delta is between 0 and 1, we should be able to find a point between a and c, we'll call that point D, such that, well, this fraction is between 0 and delta, and absolute value of f of x over f of alpha is less than delta for every alpha that's between a and d. So again, that's that idea of I can get close enough to a. If these things happen, that means you should be able to get close enough to a so that those fractions are arbitrarily small, is what this is trying to say. And notice here, remember g of c was assumed to be positive, this g of alpha is as well, but I don't know as much about f. So it's possible that this could be 0 or that this could be negative here. So I can just say that it's less than delta. In particular though, what are we going to do with it? We're going to use that to help us make more sense of this inequality, if you could say such a thing. And so what we're going to do, first thing I'm going to do is I'm going to add these to all the sides of the inequality here. And then I'm going to think about this new relationship that I've got here. I know that this is smaller than delta, right? So in fact, this inequality should still be true if I take even more away there. And then similarly here, this is, what do I have here? By that should be bigger than minus delta, so that this inequality should still be true if I took even more away right here than I did right here. What else? I've got f of alpha over g of alpha in the middle, and then kind of some more logic over here. I know that this is what's between 0 and delta, so that this inequality should still be true if I took nothing away right here, right? And then similarly here, when I added that f of c over g of alpha over, I know that this would be certainly true if I added more. If I added more to that side. And so what does that leave me with? So now we're at the point where we can say delta should be the minimum of 1, of epsilon, and of epsilon divided by the quantity absolute value of L plus 1. We don't really need absolute value there since we assumed L is bigger than 0. I'm not sure why I put it there. Just forget about it. Anyway, if that's what your delta is, then you could show that all this stuff actually unravels to saying that f of alpha over g of alpha is between L minus 2 epsilon and L plus 2 epsilon, which is pretty cool because epsilon was arbitrary. And so what does that mean? That means that the limit as x approaches a from the right of my fraction f over g is this number L. We just showed that this quantity is arbitrarily small, and so again that tells us that this limit holds. That was part A. Man, that was fun. Let's look at part B. So by the way, it's a similar argument if L is 0 or less than 0. So part B was to assume that L is infinity. So in other words, what if the limit of the derivatives of the quotient of the derivatives is infinity? Now I want to show that the limit of f over g is also positive infinity. So let's think about what that means. So that means if you were to have, say, any positive number m, say bigger than 1, and if you were to take a c between a and b, what you should be able to do is you should be able to ensure that f prime of u over g prime of u is larger than m for every u between a and c. right? So in other words, if the quotient of the derivatives goes to infinity, then eventually it should get taller than any number that you pick. Remember, that's the idea here. The graph should, I'm thinking that way. And so by the Coachee mean value theorem, such a statement like this is equivalent to saying that this sort of difference quotient, well, it's not really a difference quotient, just f of b minus f of alpha over g of b minus g of alpha is bigger than that number m, as long as that alpha and beta are between a and c, right? Those are good U's. So what do we still get to assume from this problem? We still get to assume g goes to positive infinity as x goes to a from the right. So that means we could assume a few things as before. Remember, c is like the right endpoint here. I can assume g of c is a positive number. I can also assume that c is close enough to a to ensure that this fraction is less than a half, right? If it's not, I just move c closer to a and it could happen. And what else? I'm also going to make sure c is chosen close enough to a so that g of c over g of alpha is between 0 and a half. So all of these things can be accomplished by, what I mean by all of these? All of these things can be accomplished as long as I just move c close enough to a. Alright, so that happens for all alpha between a and c. And now let's think about this kind of Coachee mean value looking thing when beta is actually equal to c. There it is, cool. And so now what we're going to do is what we just justified above here is that this quantity should be a positive number. Same idea as before. So when I multiply this inequality through by that positive number, notice the inequality doesn't change around. And what else do I know? I know that this is 1 minus g of c over g of alpha. I know g of c over g of alpha is at most a half. Therefore, this would be at least m times a half. So what we're going to focus on really is this side and this side here. So this kind of middle part is an intermediate to focus on kind of the outer two inequalities. So what we're going to do is same idea as far as simplification goes. Remember, a minus sign comes out whenever you cancel these, and then you could multiply and simplify that stuff through. So notice f of alpha should be positive now. That should be bigger than, again, the middle part, but really I want to focus on the end. Now what I'm going to do is I'm going to add this over to this side. And when I do that, I know that f of c over g of c, if this quantity is bigger than this stuff, then it should still be bigger when I take 1/2 away, right? Because what did I assume up here? I assume that, well, at worst, this is a half. So I hope that makes sense. And why is that cool? Well, what did we just show? We just showed that f of alpha over g of alpha is always bigger than, what is that, 1/2 times m minus 1. So in particular, I can find alpha close enough to a to make sure that that fraction is bigger than your bound. So in other words, it's unbounded, so that means as you get close to a, this function becomes unbounded, therefore the limit of the limit of f over g should be positive infinity as well. And the proof when L is negative infinity is super similar. It's a lot of work to justify L'Hopital's rule, this version of it. Using it's pretty easy though. So again, this version handles the indeterminate form infinity over infinity, if I didn't say that already. And similarly, minus infinity over minus infinity. So if we think about the limit of ln of x over x, we notice this has the form infinity over infinity. So L'Hopital's rule applies. And what does that tell me to do? It suffices to look at the quotient of the derivatives of each of those two functions. So 1 over x over 1. And then now, some students get super happy about L'Hopital's rule and start applying it, even when it doesn't really apply. So this form is not indeterminate anymore. It's 0 over 1. That's a fantastic number. It's called 0. So no L'Hopital here. Just rewrite this as 1 over x and think about what happens as x goes to infinity. This becomes 0.